This video is on loudspeakers and how they work, section 29.1 of the book. Loudspeakers come in a lot of different styles, sizes. This is a relatively small one for high frequencies and mid-range frequencies. These are tiny little loudspeakers that actually work across a wide range of frequencies, but don't produce a lot of sound, which is why you need to stick them right in your ear. And this is a very strange loudspeaker in that it is not designed to move air to produce sound, but to shake chairs or other wooden objects that it is screwed to. So it doesn't have coupling to air the way regular loudspeakers do, but shakes the entire body of the loudspeaker in response to electricity. So let's take a look now at a cross-section of a loudspeaker to get an idea how it works. The basic portions of a loudspeaker are the cone, which is the part that couples the movement to air. The voice coil, which is the part that actually moves. It is a coil of wire that you run a current through, and that current with the magnetic field, which is caused by the permanent magnet that's around the voice coil, results in movement of the coil. That movement of the coil then moves the cone, which moves the air. The surround and the spider are there to support the voice coil and the cone and to restore them to neutral position. They basically act as little springs to restore the voice coil back to neutral position when there's no force on it due to the voice coil getting current. And the frame is basically just to support the surround that supports the cone. Okay, so how does this work? What is it that makes this thing work? And perhaps the easiest thing to do here is to look at electromagnetism. And if we go back to sort of basic physics, we have what's called the right-hand rule. If you have a current running in the direction of my thumb, and you put it in a magnetic field that's at right angles to it, the direction of my index finger here, you will get a force that's at right angles to both of those in the direction of my index finger. So EMF, electromotive force, corresponds to the thumb, index finger, and middle finger of the right hand. What happens now if we take that electric current and instead of running it in a straight line, we run the current in a circle? Well, if we want a magnetic field at right angles to that, we're going to have a radial magnetic field. So if we've got current in a circle, magnetic field radially at right angles to it, we have E, M, taking this arrow, F, upward force. And wherever we go on this circle, the force is always in the same direction. It's always up out of the page here. And if we ran the current in the opposite direction, we'd get a force down into the page. So we get a vertical motion of this circular electrical thing as a result of the radial magnetic field. Think of this circle now as the voice coil. You've got the current running in a circle, actually a slight helix, it's a little bit of vertical motion there as well, but basically running in a circle. So we're going to need a radial magnetic field to get up and down motion of that voice coil. And we can get that from having big magnet here. The magnet is off to the sides here, pointed to by the little lines. And then having some steel or other magnetic material field pieces that concentrate the magnetic field. And the voice coil is around the steel core there. And if you take a look at right where the magnetic field pieces sort of meet the voice coil, there's a little gap there. And in that gap, the magnetic field is running through the voice coil at right angles to the voice coil. So if you think of this as a cross section, if you rotate it so that you get a nice cylindrical object here for the voice coil, you can see that you'll have a radial magnetic field always going from out to in or in to out, whichever way you've got the magnet oriented in the thing. So basically, that's all there is to a loudspeaker. The voice coil is sitting in a radial magnetic field. If you run the current through the voice coil one way, it moves up. If you run the current through the voice coil the other way, it moves down. To get sound out of a loudspeaker, you move the current up and back and forth, and the voice coil moves up and down, which, going back to the cross-section view here, if you voice coil moves up and down, that moves the cone up and down, which pushes the air up, making a pressure wave, or rarefaction wave if you pull the cone down a little bit. So you get the pressure waves in the air, which is the sound. Now, you remember I mentioned at the beginning this rather strange device which doesn't have a cone. How does it work? Well, internal to this thing, where you would have a cone, it's got a heavy weight. And basically what happens is that as you get force up and down on that weight, the inertia of that causes, the whole thing has got, by conservation of momentum, the whole thing momentum doesn't change. So if you move that weight down, the body of this thing moves up. And if you move the weight up, the body of this thing moves down. So this thing shakes in the opposite direction from the direction the weight is shaking. That isn't a big effect on something like a loudspeaker because the magnet and frame here are pretty heavy and the cone is very light. But on a bass shaker like this one, the mass that you're trying to move is actually larger than the mass of this thing. So this thing shakes quite a bit, which is the point of this. We'll, in the next video, look at the electrical models that we use for modeling the loudspeaker, because you would think it's just a voice coil, it should be just an inductor, but it turns out that's not a good enough model. And so we'll look in the next video at more detailed models.